So, welcome to the 2026 Land Aware webinar series. This is a series that we restarted in January, and it's intended that we'll have regularly scheduled webinars between January and June, taking a couple months off as people go away for vacations, and then reinitiate back in September. Our webinar series is meant to cover a range of topics, including recent case examples, innovations, communication and in landslide early warning, but also highlighting young career professionals. And you'll see that theme through our webinars as we move forward. Today, we're really happy to have with us Deanna Nash from the Center for Western Weather and Water Extremes, based out of University of San Diego, and she'll be talking today about the atmospheric river controls on extreme rainfall and landslide hazards in southeastern Alaska. Deanna, I will pass it over to you, and if you could maybe give us a bit more of an extended bio about yourself, and then I said we look forward to hearing your talk.
Yeah, thank you, Corey. So yeah, hi, I'm Deanna. I am a trained atmospheric scientist. Currently, my title is Precipitation and Geohazard Scientist at the Center for Western Weather and Water Extremes, which we refer to as CW3E. CW3E is one of the leading research centers on atmospheric rivers in the world, and that is kind of where my main expertise lies. So looking at atmospheric rivers that trigger extreme precipitation, particularly in complex terrain. So I've looked at atmospheric rivers in many different parts of the world, including high mountain Asia, Colorado, and mostly today I'll be talking about my work in Southeast Alaska. And so where atmospheric rivers result in extreme precipitation that trigger shallow landslides. So got a couple images of a couple landslides in Southeast Alaska here, and an example of an atmospheric river on the far left. So here I have a map of Southeast Alaska, which is the panhandle of Alaska, where Juneau is located. And on the map, there's a bunch of little red polygon dots that are indicating the locations of observed landslides based on the Tongass National Forest inventory. So there's been over 15,000 landslides recorded in this inventory since, I believe, the early 1900s. And, it's a widespread phenomenon. And most of these landslides are shallow landslides that are triggered by extreme rainfall. There are some examples of different types of landslides, like deep-seated landslides that have been triggered by extreme rainfall in this region, including the fatal Beach Road landslide that occurred in Haines in 2020. So I have an image there up on the right. So atmospheric rivers, that's sort of the key of this talk. Those are narrow and long regions of intense water vapor transport in our atmosphere, very much like rivers in the sky. So here I have what the atmospheric river looked like on December 2nd, 2020, that atmospheric river event that triggered the extreme rainfall that resulted in widespread landsliding, including that Beach Road landslide that I had up, the image up previously. And so here the kind of red-orange shading is indicating what we call integrated water vapor transport, or IVT. And that's essentially just telling you how much water is integrated within a column in the atmosphere, multiplied by the wind. And so it's a flux variable. So the shading here is telling you sort of like the magnitude of that water vapor strength, and then the arrows are indicating the direction of that transport. So this is a really nice kind of canonical atmospheric river feature, really looking in that river type shape. Atmospheric rivers reach Southeast Alaska pretty frequently. So this bar chart here is showing the average frequency in days per month that an atmospheric river hits Southeast Alaska. So anywhere between 8 and 15 days per month. Southeast Alaska is a temperate rainforest. They do get a lot of rain, and a large amount of their annual rainfall is from atmospheric rivers. But sort of more interestingly, is sort of this breakdown between non-extreme precipitation or less than the 95th percentile precipitation associated with an atmospheric river and the extreme, so greater than that 95th percentile precipitation, which is that light blue shading. So there's very few days per year, about six on average, about 6 atmospheric river days per year, that is contributing to up to 91% of Southeast Alaska's most rainy and snowy days. And so when we started this project, the project that I was brought on to do this work is an NSF project, Coastlines and Peoples project, where we worked with six rural and indigenous communities in Southeast Alaska to help improve their resiliency to landslide hazards. And one of the key questions that came out of this at the beginning is, well, if we have so many atmospheric rivers, we're getting so many atmospheric rivers, we hear about it all the time in the forecast, how do we know that the one coming in the forecast is going to result in extreme precipitation? If there's so many happening in very few days per year that it's resulting in that extreme precipitation, what are the characteristics, the meteorological characteristics of these atmospheric rivers that say this is more likely to result in extreme precipitation? So we did some work here in the 6 different communities, and what we found is that these atmospheric rivers that have that higher intensity water vapor transport are more likely to result in higher intensity precipitation. So starting with the figure on the left, this is just breaking down on the x-axis precipitation into percentile bins for Craig, Alaska, which is one of the communities we worked in. And then on the y-axis, breaking down that IVT or integrated water vapor transport into those percentile bins. And so I'll draw your attention to this upper right corner where you have 49% of IVT events that have greater than 95th percentile also have greater than 95th percentile precipitation. So adding these top 2 kind of rows together, about 96% of those extreme precipitation days in Craig have at least IVT greater than the 75th percentile mark. And this is pretty similar in the other 5 communities that we worked in. In the bottom right, we have this kind of box and whisker plot that's showing the distribution of IVT for each of those communities, sort of highlighting a couple different things. First is that the distributions of IVT in these communities vary pretty widely. And this sort of is really because it depends on whether they're a more coastal location, whether they're more inland. So for example, Skagway and Klukwan are pretty far north where there is less water vapor available, as well as they are both a little bit inland. So their distributions tend to be run a little bit lower. Whereas like Yakutat, Craig are more coastal locations and have that kind of higher, broader distribution of IVT. I also just want to kind of use this as a demonstration of why we focused on the percentiles. Is that, 75th percentile for Kasan, for example, is just above 400 IVT units, and then the 95th percentile just above 600, whereas in Klukwan, that 75th percentile value is about 200 IVT units, and the 95th about just under 400. And so in the atmospheric science world and atmospheric river world, there is a tendency to use like a absolute threshold for IVT to say, yes, this is an atmospheric river. That tends to be around 250. But thinking about these percentiles, maybe that's not the best approach for this, higher latitude location with this complex terrain. One of the reasons we focus on integrated water vapor transport, or it's a really useful tool for forecasting atmospheric rivers, is that it's actually really highly correlated with precipitation. And integrated water vapor transport has a higher forecast skill compared to QPF or precipitation. So the map on the right is showing the correlation coefficient for IVT and precipitation for the contiguous US West Coast. And kind of definitely along the coastline has a higher correlation coefficient, about 0.65. So pretty well correlated with precipitation there. And then the figure on the right is showing that ensemble prediction skill for IVT and precipitation. So IVT being that darker black line, and the precipitation being that gray line there. And so out to day 10, IVT will still have that higher predictive skill compared to precipitation. So it's just an extra tool we can use as a way to maybe have better situational awareness in our forecasts if we kind of use IVT. So I mentioned that one of the characteristics of these atmospheric rivers that is likely to result in extreme precipitation is that higher intensity water vapor transport. Kind of the second thing that is critical in determining extreme precipitation outcomes is the direction of the atmospheric river, the direction of that water vapor flux. And this is because in Southeast Alaska, the water vapor that is within the atmospheric river, is kind of in the lower parts of the atmosphere. Typically, most of that moisture falls below 10,000 feet. And so when that atmospheric river crosses from ocean to land, it sort of gets lifted. And then when it encounters complex topography, it's lifted even more. So then that water vapor within the atmospheric river cools, condenses, and can result in precipitation. And so when you have an atmospheric river that's more perpendicular to the topography, you're more likely to increase that lifting mechanism, that orographic lift, and increase those precipitation outcomes. And we saw this to be true in all of the communities in Southeast Alaska. So this windrose here is showing the IVT direction, or that water vapor transport direction, broken down by whether or not there was precipitation from that atmospheric river, less than 95th percentile or non-extreme precipitation, and extreme precipitation in those cyan colors. And so this is for Klukwan here. So on this map, I mentioned earlier, Klukwan is kind of further north and a little bit inland. And those southwesterly and southeasterly IVT, or pretty much southerly, atmospheric rivers coming directly from the south, moving towards the north, are more likely to result in extreme precipitation. 90% of those extreme atmospheric rivers are from that direction for Klukwan. And the results for the other communities sort of vary based on that topography, latitude and distance from the coast. But for the most part in this region, a southwesterly or a southerly atmospheric river is more likely to increase that precipitation outcomes. And so that sort of summarizes our climatology piece that we did for this project, which we as a part of working with the communities and working with the National Weather Service, we published that paper, but we also created this 2-page PDF summary that's very non-technical, that is very accessible for folks to better understand what types of atmospheric rivers are more likely to result in that extreme precipitation and trigger hazards such as landslides. So I just wanted to highlight that. So next, we're sort of going to move on to this more forecast tool that we developed with the National Weather Service in Juneau. I want to take a moment to introduce the atmospheric river scale. So I mentioned earlier that in the atmospheric river community, we typically use these absolute thresholds. I mentioned 250 IVT units to determine whether or not an atmospheric river is present. And the atmospheric river scale, which was designed at the Center for Western Weather and Water Streams, uses those absolute thresholds. So the atmospheric river scale is essentially estimating the strength and potential benefits and hazards from the atmospheric river based on the amount of water vapor overhead at any given time and how long that water vapor transport is sustained. And so the atmospheric river scale ranges from an AR1 to an AR5, where the AR5 is primarily hazardous. So you're more likely to see hazards when the atmospheric river is much stronger and lasting a longer time. So yeah, the how we sort of determine what the scale is using this box here, where you have a longer duration AR and a higher strength atmospheric river, giving you those higher values. And this atmospheric river scale which is, again, just based on that water vapor transport strength and duration, can provide a really useful first look. So I have some of our operational products from the center here. This map on the left is from an atmospheric river in November 2023 that triggered a pretty big landslide in Wrangell, a catastrophic landslide there. So we've got our low pressure here and then our atmospheric river here that's very strong, noting that it's southerly there. But if we translate what's going on in this map over here to our atmospheric river scale, we're seeing that the maximum observed atmospheric river scale for this event was just an atmospheric river scale 1 to 2, which, going back to this, is just saying mostly beneficial, but be hazardous. And we were feeling, we as in me and the National Weather Service forecasters, that maybe this wasn't necessarily communicating the potential impacts that could be coming up from a storm. That if someone, maybe from the public that looked at this, could say, oh, well, it was just an atmospheric river scale 1 or 2, it's not really anything to be worried about. So we wanted to design something, another tool separate from the atmospheric river scale, that incorporated what we found in our climatology analysis and could help forecasters improve their situational awareness ahead of these impactful events. I have a little bit more here, kind of diving into the atmospheric river scale. So this is looking at like the historical, because I did just show you one event here, but if we look at the historical classification of atmospheric river scale events near Haines, Alaska, we found that there's historically mostly AR scale 1 and 2 events with a couple AR scale 3 events. And there have never been, I guess up to 2024, an AR scale 4 or 5 observed. And again, that's because it uses this absolute threshold, not a percentile based threshold. And this location is, very far north and inland. And so again, looking at this December 2020 event, which resulted in that deep-seated landslide, this chart here is showing the black line is the integrated water vapor transport for that event, and then the shading is indicating where it was identified as an AR scale 2. But if we add on these percentile markers, so these 50%, 75%, and 95% are showing those percentile values for Haines, this event well exceeded the 95th percentile. So it was a very extreme event, as well as a quite long duration event. And you also have this little blip here that happened a couple days prior that exceeded the 75th percentile, but wasn't categorized as an AR scale event at all. And that's sort of important context for this event. So this short duration event was actually a light snow event that preceded this event. So thinking about multiple events in a row, saturated soil, these are things that add up to result in more widespread hazards and impacts. So me and Aaron Jacobs at the National Weather Service, we set out to build what is called a model climate for this region. And so what model climate does is essentially it's really just pulling historical values from the same location and the same time of year, and creating those percentile values for each grid cell. And this is an example of what that model climate value looks like. So the shading is indicating the percentile rank of that integrated water vapor transport, and the black contours are showing the integrated water vapor transport, the forecasted value. And the cool thing about model climate is that it's not just, one model climate percentile rank value for the day of year. It also takes into consideration lead time. So here this is looking at a forecast that was initialized about 4 days prior to that really impactful event on December 2nd. And so here that really dark green shading is telling us that those water vapor transport values at a 4-day lead time are about the 99th percentile, so very extreme. So starting to give some of that context at a 4-day lead of how extreme this event is likely to be. And this is really just building on that AR scale component. So we've this first piece of just that percentile rank is saying how strong the water vapor transport is, but then we want to include how long the water vapor transport is sustained over a region, because if it's a longer duration, it's more likely to result in extreme precipitation. And so then we get what we call a situational awareness table. So this, I apologize for the tiny values. It's just, I would recommend kind of focusing on the color shading. And so this table here is like starting at the top, is initialized on this 28th of November, 2020. And then it's what is the maximum IVT rank value within this little black box every 6 hours out to 168-hour lead. And so looking at the situational awareness table, a forecaster could, for example, pull out a couple things. The first is that, oh, well, we're having kind of a short duration but high intensity event, followed by pretty quickly a much longer duration, high intensity event in Southeast Alaska. And so it starts to, for the forecaster, build that situational awareness of, oh, we're having multiple high intensity events in a row. One's maybe a shorter duration than the other. And that this is really cool. And so we actually compared our percentile ranks for all landslide events that we knew the timing of very well, kind of down to the day, based on a USGS newsworthy landslide database, as well as the NOAA National Weather Service storm reports. And this left bar chart here is showing you the distribution of those model climate percentile ranks. And the x-axis is the forecast lead time in hours. So the first column is that 24-hour lead, all the way out to the 168-hour lead. And so one thing I notice is that out to about, I believe it's out to about a 4-day lead, the days that the atmospheric river days that had observed landslides, the model climate IVT rank was greater than the 95th percentile. And we compared this to all the other days without landslides, and the distributions are quite different. So you have a little bit more confidence that this is pretty useful. Just this IVT percentile rank alone. The next kind of sort of piece I want to talk about is the freezing level. And so I'll break that down a little bit. So I've got a little schematic here provided by one of my colleagues. So thinking about that atmospheric river moisture kind of coming in and encountering that topography and getting lifted by that topography, you're resulting in precipitation. But where you have the height of the freezing level, or that where it transitions from 0 degrees Celsius and cooler, below that, you're going to have rain, and above that, you're going to have snow. And so increases in that temperature are going to lower the height of the freezing level, which will decrease the amount of snow and increase the amount of rainfall. So when you have cooler temperatures, you're more likely to see increased snowfall, even at higher elevations, versus warmer temperatures means higher freezing levels and increased rainfall. This is really important because atmospheric rivers are full of moisture that is warm. They're warm. They are typically very warm features. Water vapor tends to be warmer. And so in this case, we wanted to see, well, do the kind of model climate percentile ranks for that freezing level show up in this forecast tool? And it certainly does, especially for this December 2020 event. So that higher model climate freezing level rank, so the darker red shadings, indicates a potential for higher fraction of rain to snow. And again, this is the model climate tool initialized at a 4-day lead. So at a 4-day lead, combining with our integrated water vapor transport on our situational awareness table, we see some pretty cool things. So the first, if you recall that like shorter duration storm, here the freezing level ranks were below the 75th percentile, which indicates a cooler storm. And then that longer duration storm, that one that resulted in the impacts, has freezing levels greater than the 95th percentile, and was a much warmer storm. And if we compare this to some of the observations that were taken, this is a figure from Darrow et al., where this blue line is the temperature at one of the stations close to the Haynes That Beach Road landslide. The purple is the snow depth, and the green is the snow water equivalent. If we kind of hone in on this December 2nd time frame, we see a huge spike in temperature that coincides with the incoming atmospheric river. A really dramatic decrease in snow depth, so about 40 centimeters decrease in snow depth, even though SWE was increasing because they were gaining some precipitation at the time. This is really important because this is saying that that increase in temperature, maybe there was an increase in rain, but more importantly, there was a decrease in snow depth. So it's sort of that rain on snow component that this freezing level part of this model climate tool is getting at. So it's increasing awareness of whether or not an event is likely to be a rain on snow event, increasing that soil saturation when you have that snow melt, increasing the risk of landslide. And again, coming back to these histograms where we compared days with landslides and days without landslides, the results aren't as compelling as the integrated water vapor transport, but they're still very interesting. So about 50% of those landslide days had a freezing level greater than the 90th percentile. So we're not necessarily this isn't happening every single event. We're not always having rain on snow events, but this is an important thing to consider, especially in the cooler season, October to March, when you might have snow on the ground and you get a really warm atmospheric river coming in. The third kind of variable that we looked at in terms of whether or not it could result in impacts was low level wind. So when we went to the communities, we talked to people, a lot of folks said it is incredibly windy during these events that trigger landslides. Can you see what you can find out? And we found out that a higher model climate low level wind rank does indicate potential for more wind related hazards. So again, I have this map showing the model climate forecast at a 4-day lead for that December 2nd event, where you have greater than 98th percentile low level wind rank for that time. Bringing back our situational awareness table, focusing on that second event. The first event did have high wind, but the second event had high wind ranks as well. And sort of as you start to add all of these variables together, essentially, I like to think of it as like a jar that you are filling with marbles, and each component is a marble that's maybe increasing the likelihood of a landslide here. So we've got high water vapor transport, check, long duration water vapor transport, high freezing level, high winds. So each sort of piece that you're adding is adding a marble to the jar that maybe a slope that has susceptibility to failure has at one point it will have too many marbles and it will overflow and will fail. Looking at these box and whisker plots for days with landslides versus days without, again, this is really quite compelling, similar to the integrated water vapor transport, where we see more than 75% of landslide days had low level winds greater than 95th percentile rank. And that does go out to, honestly, almost 120-hour lead. So we're seeing much longer lead times where we have this situational awareness of potential for landslide activity. And then the last piece in this model climate tool is this is precipitation, is QPF. So we wanted to make sure that not all high IVT atmospheric rivers result in precipitation. So we wanted to include precipitation in this tool as well. So again, we're looking at the model initialized on the 28th of November at a 4-day lead time for that December 2nd event. And here we have, I think, a maximum percentile rank for QPF all across the northern panhandle here. And then again, combining that with our situational awareness table, I've also added in a column that's the duration that the IVT is sustained greater than 95th percentile. So you get you're kind of getting that cumulative piece as well. So like, for example, on December 2nd, IVT had been greater than the 95th percentile for at least 48 hours. And so this is super helpful for our forecasters, especially at this long of lead time. And then back to these box and whisker plots. This is also super robust results showing that, again, about 75% of those landslide days had precipitation greater than the 95th percentile. I mean, in some cases, much higher than the 95th percentile. And this extends out to those long lead times, again, about 120 hours as well, compared to this distribution of days without landslides. So I like to wrap up this kind of model climate piece in thinking about all of these different variables, all these different marbles that I talked about, where the AR scale had that water vapor strength and duration included in that calculation. But there are many other variables, such as the freezing level or the rain-snow transition height, that low-level wind strength, precipitation intensity, as well as the direction of that IVT, that water vapor transport, and the direction of the low-level wind, that are all combining together to determine whether or not we're going to have that really high more likely to have higher precipitation and more likely to increase the likelihood of those hazards. And we took all of these and created what we call the AR hazard index. And it is on a scale of 1 to 5, but this is based on those percentiles, based on that model climate, and again includes all of these components. So not just two, but it's a multivariate index. And here's what the AR hazard index forecasts look like on December 2nd, 2020, at a 96-hour, a 4-day lead. So here, this is showing that you're getting an AR hazard index widespread 3s, one single little 4, definitely 2s across the northern panhandle. And what we did is we partnered with the National Weather Service to create this potential precipitation impact table that aligns with this AR hazard index. This is a really shortened version, but the idea is that you're not likely to see impacts. There's some really localized minor impacts at these lower values. And then as you increase, the yellow indicates possible isolated landslides, the orange indicates isolated landslides, etc. And the National Weather Service, this is one tool that they've been using to inform their messaging in their flood watches and warnings. So they have the ability to put messaging like chance of isolated landslides in this region in their messaging in the flood watches and warnings when they put those out. And so this is just one tool that they have at their disposal that sort of helps inform that messaging that they're putting out. And then I did want to just zoom in on Southeast Alaska at that same lead time, just noting some of the spatial variability. And then again, the forecast will change as time changes. So this is what that hazard index forecast looked like at a 24-hour lead. So at a 4-day lead, maybe they were messaging, a watch, and it changes at a 24-hour lead. I actually have no idea what the time progression was of the watches and warnings for this event, but this is just a proof of concept that for this event, if they had this tool, it could have assisted in that situational awareness in the messaging that went out ahead of time. And then to kind of summarize this model climate piece, we looked at the percent of landslide days that met kind of all 3 of these thresholds. So low level wind, precipitation, and water vapor transport greater than or equal to the 95th percentile. So this is about, yeah, we had about 120 unique landslide days that we looked at. Again, the x-axis is showing that lead time in hours. So about 90% of landslide days had these combined extreme conditions. So this is very important. It's the fact that it's the combined conditions kind of cumulatively adding to that hazard risk. And if we compare that to the percent of non-landslide days, which is a lot more, only about 30% of non-landslide days had those combined conditions. And I do want to note that we only had 120 observed landslide days, but there were likely some of these non-landslide days that possibly had landslides. Landslide reporting is challenging in this area. So for the next and kind of final chunk, I'm going to talk a little bit about the work we did thinking about the changing climate. So here I have an image from Darrow and Jacobs that is showing the number of landslides reported in Alaska since the 1880s. And I noticed that and the colors are indicating so the like pink shading is total number of landslides, and then the three colors is breaking down that pink bar into what they were associated with. So rain, freeze thaw, and warm environment. So most of these landslides were triggered by rain, and you've got a couple freeze thaw and some warm events here. But more importantly is we're seeing that the frequency in reported landslides, has dramatically increased since the 1980s, and some of the most fatal landslides have occurred within the past 5 years. So thinking, well, we've already seen increases in temperature, changes in precipitation due to climate change. We're already observing the impacts of climate change in this region. What can we expect in sort of the near future in terms of these extreme conditions that are likely to trigger these extreme meteorological conditions that are likely to trigger these hazards? A lot of work has already been done on kind of quantifying the changes in atmospheric river frequency and intensity across the globe. Here I'm showing North America. So this is a figure from Payne et al., where the pink shading on this map is indicating from a bunch of different studies that have been done that all agree this is where we're likely to see increases in the frequency of atmospheric rivers. And of course, this box is covering Southeast Alaska, but the pink is there. So there's definitely will be an increase in the frequency of those atmospheric river events. In addition, there is projected across North America an increase in snow ice melt, an increase in precipitation, which is going to lead to an increase in flooding and an increase in extreme precipitation. There is some uncertainty in the projections. So from study to study, there's definitely differing results. But overall, we're expecting that those atmospheric rivers are likely to become more frequent and intense, resulting in extreme precipitation and hazards related to that. And so to kind of build on this and to build on that percentile, like extreme meteorological component framework that we used for the model climate, we used a high resolution, a 4-kilometer resolution weather model to compare past extreme conditions from 1980 to 2019 with projections for the mid-century, so from 2031 to 2060. And we looked at these changes for these 4 of these variables that were included in our model climate tool to sort of say, okay, here's how we expect the distribution of that 95th percentile to change in the near future. And what we found here, this map is showing the change in the integrated water vapor transport that's greater than 95th percentile across Southeast Alaska. So this is the difference between the future and the historical. And this is based on the CMIP-5 model. And this is the CCSM, specifically the CCSM model, and using the RCP pathway 8.5. So what that means is that this is just a single model result. So it's not showing the kind of the distribution between the models. This is just one of the more likely future results, and that RCP 8.5 just sort of means business as usual. So it's a pretty good representation of what to expect in the near future. And what I see is that there is a really dramatic increase difference in that integrated water vapor transport, especially in those lower latitudes. So we can expect that our extreme events are going to get more extreme in terms of water vapor transport, low level wind, as well as our freezing level. So all of those things that I just talked about, the 95th percentile value, that 95th percentile value is going to increase sort of across the board in all three things. And so this is sort of indicating that we're likely to see warmer storms with more rain and less snow. And I did quantify those changes in extreme precipitation shown here. So precipitation extremes are likely to be about 12 millimeters per, up to 15 millimeters per day more extreme compared to the historical period. While looking at changes in extreme snow water equivalent, we're seeing browns here, so that's indicating a decrease in that snowfall. So we've got our warmer storms, our wetter storms that are likely to increase that extreme precipitation as well as increase those hazards. Bringing it back to that freezing level component, thinking about as those freezing levels rise, it's more likely that that precipitation is going to fall as rain. So we saw an increase in extreme precipitation. And because of that increase in freezing level here, we're anticipating that more precipitation will fall as rain, especially at higher elevations, which is going to increase that likelihood of rain on snow events. Those rain on snow events are melting the snow, rapidly adding more water to the landscape in addition to what is falling as rain. So increasing that hazard. So here I have a map showing the frequency, the average frequency in days per year of rain on snow events in Southeast Alaska. So kind of in these mid-slope areas is where we're seeing those higher rates of rain on snow events. And then the points here are the locations of those newsworthy landslides that I mentioned that we know the timing of. And if it's colored in yellow, it was associated with an atmospheric river. And if it has a little red outline, that is a rain on snow event that we observed. So I guess looking at this map, it's like, oh, well, there's not that many rain on snow events. They're not that frequent. But if we compare the number of rain on snow related landslide days to the number of rain on snow event days, that fraction is much higher compared to AR related landslides compared to atmospheric river days. So these rain on snow events are producing landslides at a higher rate than just atmospheric rivers alone. Atmospheric rivers are related, but we are concerned about the frequency of those rain on snow events. So then how are they going to change in the future? This map here is showing the change in the rain on snow frequency. So we are seeing an increase up to 3 days per year of rain on snow events in these mountainous regions, a little less common on the southern coast. And then if we also look at the change in rain on snow intensity for the future, we are also seeing an increase in that intensity. So even though they're relatively kind of infrequent, they are events that are more likely to result in landslides, and they are expected to increase in the future. So this is just something to consider when it comes to landslide awareness. So to end, overall, stronger atmospheric rivers or atmospheric rivers with more water vapor in them, combined with heavier rain and reduced snowfall, is likely to increase that landslide and flood risk. And this really highlights the need for improved early warning systems as well as community preparedness across Southeast Alaska. I've put my email up here as well as some QR codes to, this is our paper on the far right, the non-technical summary that I highlighted, so that 2-pager, the QR code to that atmospheric river hazard tool. So we have it available operationally, so you can go on the webpage and kind of dig into the forecast, as well as on the far right here, the paper that's looking at the climate change results that I just went over. Thank you.